In the last video, I showed how to derive this equation, Snell's law of refraction, from the fundamental postulates of ray optics. In this video, I will show how to generalize our result to 3 dimensions. I should say that this process does get a bit complicated at points, so feel free to pause the video every now and then, and think about how each step makes sense. So, how could we go about this? Well, in 3-dimensional space, positions and orientations are conveniently described using spatial vectors. So let's define a unit normal vector n hat, perpendicular to the boundary between our two media at the point of intersection. Let's also define a unit vector s1 hat, pointing in the direction of the incident ray, and a unit vector s2 hat, pointing in the direction of the refracted ray. Okay, but now what? Well, our original equation obviously contains these sine functions, and we know that the magnitude of the cross product between two vectors is the product of their individual magnitudes times the sine of the angle between the vectors when they're placed tail to tail. So let's take a look at the cross product between n hat and s1 hat. Since these two vectors both have unit length, their cross product has a magnitude equal to the sine of the angle of incidence, theta 1. Analogously, the cross product between n hat and s2 hat has a magnitude equal to the sine of the angle of refraction, theta 2. We can also see that both cross products point in the same direction, as determined by the right-hand rule, and we can safely state that the following equality must hold. We have thereby already found a vector form of Snell's law. It is not very useful in its current form though, since even if we knew the refractive indices, the direction of the incident ray, and the normal vector, we wouldn't be able to just plug these in and solve for the direction of the refracted ray. We will need some tricks in order to isolate s2 hat. When faced with a problem like this, it is sometimes useful to just try some allowed operation and see what happens. We could, for example, try taking the dot product of both sides with the normal vector, but since both our cross products are perpendicular to the normal by definition, we just get 0 on both sides. So let's instead try taking the cross product of both sides with the normal. If we look at the left-hand side first, we can see that this resulting vector must in fact be perpendicular to the normal and parallel to the plane of incidence at the point of intersection. What's more, the magnitude of the cross product of two perpendicular vectors is simply the product of their magnitudes, and the normal has unit magnitude. So the magnitude of this double cross product is just the magnitude of n hat cross s1 hat, which we already know equals the sine of theta 1. If you think about it, this means that we have actually found the component of s1 hat perpendicular to the normal. We can use an analogous argument to show that this vector on the right-hand side is the component of s2 hat perpendicular to the normal. We can then attempt to isolate this component. We can do this by writing the perpendicular component of s1 hat as s1 hat minus its parallel component. This parallel component can then be written as the dot product of n hat and s1 hat times n hat. This means that we have managed to express the perpendicular component of s2 hat in terms of known quantities only. If we can somehow do the same for its parallel component, we can simply take their sum and we're done. Let's begin by writing s2 parallel as its magnitude times n hat. We can then use the Pythagorean theorem to write the magnitude as the square root of the difference between the squared magnitude of s2 hat and the squared magnitude of s2 perpendicular. But s2 hat has unit magnitude, and from earlier we know that s2 perpendicular can be expressed in terms of s1 perpendicular. We can now use the Pythagorean theorem again to rewrite the magnitude of s1 perpendicular, and the resulting difference between squares can then be simplified to 1 minus the squared dot product of n hat and s1 hat. We have thus succeeded in our goal of expressing both components of s2 hat in terms of known quantities, We can now take their sum to get this final expression for S2 hat. If you think this looks a bit messy, I don't blame you. But the significance of this formula is that we now have a direct way of computing the exact direction of the refracted ray from the direction of the incident ray, provided we also know the refractive indices and the normal vector. Also, a computer doesn't mind at all that the equation is a bit clunky. In fact, I have used this exact equation to create a MATLAB application called Lens System 3D, which can be used to accurately simulate simple versions of optical instruments such as telescopes, microscopes, and telephoto lenses. The program is intended for use in undergraduate optics education, but if you have access to MATLAB and want to check it out, I'll leave a link in the description. The application is also open source, so anyone who wants to can take a peek under the hood and see how the code works. With that said, this is where I'm going to end this two-part series on Snell's law. If you enjoyed these videos, consider subscribing and keep an eye out for future content.